Today's lesson is going to be on Taylor series and the approximations and the error involved in the approximations. So first I just kind of want to talk about error and what that means, and then we'll get into the specific cases. So let's say we have some function and we want to write a Taylor polynomial with a specific center. So we use A as that center. So we write a Taylor polynomial, and it's going to match pretty close at A, but as you get further and further away, it may not match as good. So there's two things involved in the accuracy. We're looking at a value not A, but something a little bit farther from A. And the distance between the actual function and our Taylor approximation is our error, or sometimes you'll refer to as a remainder. There's two things. Either if the degree of the polynomial gets higher and higher and higher, that error will be less and less. And the farther away from A you get, the error will be more. So the closer you are, the error will be less. The farther, the error will be more. There's two ways that we can calculate error. And those are going to be our two topics for today, the alternating series error bound and the Lagrange error bound. So first we're going to talk about the alternating series bound, which we've already seen, which says that if you have an alternating series, the maximum value of the error is going to be less than or equal to the next term in the series. Okay. So we're going to investigate this with sine of x. So first thing I'm going to do is find sine of x, and then I'm going to evaluate it at 0, 0.25, 0.5, 0.75, and at 1. So I'm going to use the calculator to do this. So I'm going to put sine of x in my y equals, and then I'm going to use the table. So if I go to second table set, I'm going to start at 0, and I want to go up by 0.25. Now if I go to the table, we have the values at 0, 0.25, 0.5, 0.75, and 1, and we're going to put those on our notes. Okay, so those are the actual values for sine of x. Now what we're going to do is look at the Taylor series approximation. The Taylor series for sine, remember, is the odds. So it's going to be, degree 3 is going to be x minus x cubed over 3 factorial. Now we're going to plug those same values into that polynomial, again using the calculator. So I'm going to plug it into my y equals, and the factorial you can find under the F2 function menu. I'm going to go back to the table, and these are the values of our third degree polynomial. So for the third degree polynomial, these are the values we get, and what you should see is they're actually pretty darn close to the actual values. Those are the same. That's a little bit off, this is a little bit more off, this is a little bit more off, but they're still pretty good. Now we're going to do this with a fifth degree polynomial. So we're going to add on one more term, plus x to the fifth over 5 factorial. Again, we'll plug this in the calculator. So we'll add x to the fifth divided by divided by 5 factorial, which is 120, or we can do 5 factorial. Okay, we'll go to the table and put those values into the chart. So our error here it's even closer. So here it's pretty much the same, here it's pretty much the same, here it's a little bit off, but it's closer than this one, and same thing here. So as a follow-up, describe the change in accuracy of the polynomial approximation as the distance from the point where the polynomial is centered increases. So basically, the farther you go from the center, which in this case is 0, the less accurate the approximation is going to be. It says to use the error bound for the alternating series to find the error using sine 0.5. So the error is always going to be less than the next term in this sequence, which in this case is going to be 0.5 to the 5th over 5 factorial, which if we plug that into the calculator is going to be 0.0002604. Okay, we're going to compare that to the actual error, which is going to be sine of 0.5 minus that guy. Okay, so if you do this in the calculator, you're going to get 0.000258 So this is the bound for the error is 0.00026. The actual error was slightly less than that. Okay, next one, we have an alternating series. So when we're asked to estimate the maximum error of cosine of x from -0.2 to -0.2 to 0.2, we're going to look at the next term. So the error is going to be less than or equal to the next term evaluated at 0.2. So that's going to be 0.2 to the 6th over 6 factorial, which is a very, very small 8.889 times 10 to the -8. So that is a pretty close approximation at that point. Okay, we're going to determine the degree of the polynomial required for the error approximation of sine 0.3 to be less than 0.001. Okay, so sine of x, again, is just going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So I'm just going to create a chart here with the degree of the polynomial and then the error, which will be given by the next term. So if my degree is 1, the error is going to be approximated by the next term in the sequence, evaluated at 0.3. So that's going to be 0.3 cubed over 3 factorial, which is 0.045. So that error is too big for us. So we're going to go to the next degree, which in this case has to be degree 3. We're not going to have a degree 2 polynomial, which means my error is going to be 0.3 to the 5th over 5 factorial, because that would be the next term, which gives me 0.00002, which is good. That is less than 0.001. So if I have a degree 3 polynomial, it meets that constraint. Okay, so our next question, again involving sine. So for approximately what values of x can you replace sine of x by x, the third degree polynomial, x minus x cubed over 3 factorial, where the error is no greater than 5 times 10 to the -4. So we've said the farther you get away from the center, the less accurate the approximation is going to be. Here we're looking for how far away can we get where this will approximate this with an error of less than this. Okay, well, if we have the third degree polynomial, that means my error is going to be approximated by the next term, x to the 5th over 5 factorial, and we want this to be less than or equal to 0.0005. Okay, that's 5 times 10 to the -4. Okay, so we're just going to solve this and then I'll deal with the negative. So I'm going to multiply this by 5 factorial, which is 120, which gives me 0.06. And then I'm going to take the 5th root of that. Okay, so I get this. So the values, 5, 6, 9, 7, I can get as far away as 0.5697 and still have an accuracy of 5 times 10 to the -4. Okay, we're going to confirm this graphically. So in my y equals, I'm going to have the error, which is going to be the difference between sine of x and the approximation at the polynomial. And then I'm going to compare that to 0.0005. So for my window, I'm going to go just from -1 to 1, because we already know our answer is going to be about 0.5. And then for my y's, I'm going to go from 0 to 0.001, because that'll put the 0.005 right in the middle. I actually want to look at the absolute value of the error. So now when we graph it, we'll get both sides. Okay, and if you calculate these intersections, it's going to be our -0.569 and our positive. Okay, so let f of x equal 1 over 1 minus 2x. Write the first 4 terms and the general term of the series generated by f of x centered at 0. So our a1 is 1. And then our r is 2x. So we're going to have 1 plus 2x plus 4x squared plus 8x cubed and so on, which will be 2x to the n. The interval of convergence is when 2x is between -1 and 1, so -1/2 and 1/2. So now we're going to investigate this at -1/4. So find f of -1/4, which is going to be 1 over 1 minus 2 times -1/4, which is going to be 1 over 1 plus 1/2, which is 3/2, the reciprocal of that being 2/3. Okay, then we're going to find how many terms are adequate for approximating the error not exceeding 1% of magnitude. So if my actual value is 2/3, 1% of that is going to be 2/300 or 1/150. There's different ways to do this. I'm just going to simply write out the terms of the series until I get to one that's smaller than this. So this is going to be 1 plus 2 times -1/4 plus 4 times -1/4 squared and so on. Now you can use the calculator. You're just going to be multiplying by 2 times -1/4, so -1/2. So I'm going to have 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus 1 over 32. Okay, we're getting close. 1/28. The next one is 1 over 256. So since the error is approximated by the next term, that's how many terms I need to be that accurate, because this would be my error, and my error would be less than 256. So this is 1, 2, 3, 4, 5, 6, 7, 8 terms that we need to add. Okay, and what is the approximate value of cosine 1/2 obtained by using the 4th degree Taylor polynomial series for x, cosine centered at 0? Cosine of x is our odds, our evens, so 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So we're evaluating this at 1/2. So cosine 1/2 would be 1 over 1/2 squared over 2 plus 1/4 to the 4 over 24, which is going to be 1/2 squared is 1/4 divided by 2 is 1/8. And then you're going to have 16 times 24, which is 384. Okay, so that is the alternating series bound. Next, we're going to talk about the Lagrange error bound.